Okay, so next we are going to prove proposition 8 to 6. So let's start by recalling its statement. And the statement was this: X is any set, finite or countable or uncountable, X is any set, and we have two real valued functions f and g defined on X, such that these two series and summation of g of x are absolutely convergent. Okay, so this is the setup. Then there are four parts. In part A, the claim is that this series is also absolutely convergent and its sum is equal to, that is, its value is equal to the sum of the first series plus the sum of the second series. So that is part A. Then in part B, we multiply the series by a real number. If C is any real number, then this series is absolutely convergent and its sum is C times the sum of this original series. Then in part C, we write X as a union of two disjoint subsets, that is x1 and x2 are disjoint, that is their intersection is the empty set. If that is the situation, and this of course is given to be absolutely convergent, then these two series are absolutely convergent and the value of this series is the sum of the values of these two series. That is one half of part C. There is another half. And plus okay, so that is one half of part C. and the other half is this. Conversely, if say you have a function h, again a real valued function defined on the set x such that these two series are absolutely convergent. Then the entire series of all the h values as x varies over x is absolutely convergent, and the sum of all the h values as x varies over x means x1 union x2 is the sum of these two values. And there is another part D. In part D, we have another set y. I mean, we already have x, but say there is another set y, and we have a bijection phi from y into x. Then this sum is absolutely convergent and its value is equal to the value of the original sum. Okay, so that is the entire statement of the proposition. Now we are going to start the solution in which we are going to prove these things. But we will not prove all the parts today itself. We will prove only parts A and B. Parts C and D we will prove next Sunday. So let's now start the solution. So our hypothesis is that those two series, summation of all the f values and summation of all the g values, they are given to be absolutely convergent. So we start off like this. Let S1 be the supremum of this set and S2 be the supremum of the corresponding set for the function g. Since it's given that the two series, that is sum of f of x and sum of g of x, those two series are absolutely convergent, S1 and S2 are real numbers. In fact, they are non-negative real numbers. That is, they are finite. Since summation of g of x as x varies over x are absolutely convergent, we have S1 and S2 both in the set of real numbers. So, for any finite subset A of x we have. So now we look at this finite sum. Since this term is less than or equal to the absolute value of f of x plus the absolute value of g of x, so this finite sum will be less than or equal to this. In other words, for each element x in A, we are considering the triangle inequality involving these f and g values at that point x. And we are adding up all those inequalities. That gives us this inequality. Okay. Now, since this is a finite sum, we can write this as a sum of two sums using properties of finite sums, that is, this is equal to this sum plus this sum. Okay. Now see, this is one element of this set and S1 is the supremum of this set, that means the least upper bound. So this arbitrary element will be less than or equal to S1. Similarly, this one will be less than or equal to S2, and it makes sense to add S1 and S2, I mean the inequality that we are now going to write. That will be just this. This thing is less than or equal to S1 plus S2. Now, S1 plus S2 is meaningful because they are real numbers and not infinity. Okay, so this thing is less than or equal to S1 plus S2. But this is true for any finite subset A of X. So when you vary A over the collection of all finite subsets of X, all such sums have S1 plus S2 as an upper bound. So the least upper bound of all such sums is going to be less than or equal to this upper bound S1 plus S2. So we write hence the supremum of this set where A is a subset of X and A is finite is less than or equal to S1 plus S2, and hence definitely this supremum is less than infinity. And hence by the definition of absolute convergence, now we can say this. This implies this sum is absolutely convergent. Okay, but that is just one half. We still have to prove that the value of this sum is the value of those two sums taken, I mean their sum of those two values. Now, so now we are going to look at what the value is. Now, since okay, let me write like this here. The set of those elements in capital X for which f of x plus g of x is not equal to 0 is a subset of this set union g of x is not equal to 0, and since that union of course itself is a subset of X, we have, okay, so now we are going to start with this and we have to show that the value is equal to the sum of all the f values plus the sum of all the g values, but every step has to be properly justified. Okay. Now, what is the definition of this sum? I mean, what is the definition of its value? Since we have proved that this is absolutely convergent, by the definition of the sum, the value of this sum is the value of this sum. Because we know that since this is absolutely convergent, this set that you see here is an at most countable set. So by definition, this sum has the value which this sum has. Okay. Okay. Now what we write, this is equal to this sum. Watch carefully. In place of f of x plus g of x being non-zero, we are going to write this. But why? I mean, how? What is the justification? The justification is just this. See the solution to the previous y exercise. That's why we did it. In that y exercise, besides addressing those issues that are there regarding the two definitions of absolute convergence, we did one or two other things, right? One of them helps us here. Okay. Now we need to understand how we get to this step. I mean, how we get to this conclusion, and that is what is the justification of this step, and also in exactly what way is this y exercise helping us. But even before going to that, let us see, I have not really said why we have this inclusion. No? So here what we are claiming is that if you take any element from this set, that is an element for which f value plus g value is non-zero, then it has to belong to this union. That means it should be an element for which either the f value is 0 or the g value is 0, or non-zero, or the g value is non-zero, or both are non-zero. Why? Because if that is not the case, then for that f value as well as g value are both 0, but then the sum has to be 0. So that's why that x, if it is here, then it must belong to either this set, or of course both. That's how we have this inclusion. And this union is of course obviously a subset of x. Okay, now let's go back to that thing. I mean the solution to this y exercise, one particular part of this solution. You remember we ended the solution by doing something. So say you have this f is not this f, okay? You just simply consider this sum where f is some function defined on a set x, whatever that set x is, such that this sum is absolutely convergent. Okay. Now say y is the set of those points in x at which f does not vanish. In fact, we need this set in order to define the value of this sum, just like what we did here in this step. So y is the set of those x at which f does not vanish. Then by definition of the value of this sum, this is equal to the value of this sum, where due to the fact that y is at most countable, this value has its own meaning, which comes from the first definition of absolute convergence. If y is finite, then this is just a normal finite sum. If y is countable, then you choose any bijection from n into y and then use that bijection to turn this sum into an ordinary infinite series. That series is absolutely convergent, so it will have some real number sum. That is the value of this, and hence also the value of this. But towards the end of this y exercise, we proved that if you have an intermediate set z or z, then regardless of what the set z is, this series will also be absolutely convergent, where x varies over this set, intermediate set, and will have the same value. That's what we have used here in this step. What is our y? Our y here is this. Because that y should be this now. What is our function? F of x plus g of x. So we are considering those points in x at which f plus g does not vanish. And our z, this intermediate set here, is this union. And you can see that's why I have written this is contained in x. So y is contained in this z or z, and that is contained in x. So that is why the sum, see, this is the original sum. Compare this with this one. This one is this middle sum, and this one is this sum. Okay, the values will be the same. So this is where we are taking the help of the previous y exercise. So now we can work with this sum only. Okay, because writing these conditions is equivalent to varying our independent variable over this union. Either f of x is 0 or g of x, why do I keep saying 0? Either f of x is non-zero or g of x is non-zero. This or represents the union. Okay. Now what do we do? Now note that the set that you are looking at here is at most countable. Why? That is because our original series, both of them are absolutely convergent. Both these series are given to be absolutely convergent. So by that previous result, this is at most countable due to the absolute convergence of this, and this is at most countable due to this being absolutely convergent. So their union is of course also at most countable. So the sum that we are looking at now is a sum over a set that is at most countable. That means this set, that is this union, is either finite or countable. And that is why on this sum we can use properties of finite sets, properties of such sums over finite sets, and properties of sums over countable sets. And those things we already have at our disposal. So now the next step is this. One of those properties says that the sum of f of x plus g of x is the sum of the f values plus the sum of the g values. So first let us write that, and then we will write the justification within brackets. We have taken the sum of the f values, but we have kept g of x not equal to 0. That is because we are not changing the set over which we are considering the sums. We are just simply writing this sum as a sum of two sums plus and the elaborate justification here is just I need to recall the numbers by proposition 7.1 11 part F and propositions 7 to 14 part A, since this set union is at most countable. Okay, so that is the justification. In this proposition, we have that, in part F, you have that property of finite sums. So when our underlying set over which you are considering the sum is finite, because it's at most countable, it may be finite also. In that case, you apply this proposition. And when this set is infinite, that is when it is countable, then you apply this proposition, which is that corresponding result for sums over infinite sets, that is sums over countably infinite sets. Okay, so we have got till this. Now in the next part, we just simply we won't write g here in this sum, plus in this sum, this is g. We won't consider the condition on f values. In place of this, we have written this, and in place of this, we have written this again. Why? How? What is the justification? And that justification is the same thing. By, or what did I write there? See the solution to the previous y exercise. But let us look at it more closely. Exactly how are we getting this thing equal to this thing? Now we understand, we have some idea of how that is happening. There should be some z, some x, those sets, but exactly what sets and exactly how. See, the thing here is this. Okay, let me just write it here itself. You see, when you are considering this sum, by this sum, what I mean is this. Say you are considering this sum. By definition, this sum is equal to this sum actually. So your original set is x, and that y set here is the set of those values of capital X at which f does not vanish. And along with that, if you also include this in the sense as a disjunction, not using and, not a conjunction, but as a disjunction, or that is, you take those values of, in other words, you are just considering this set. That set, that union. Then the sum corresponding to that union, that means where x varies over that union, is this first one, this one. And this union definitely contains this as a subset, which is our set capital Y. And that intermediate set Z or Z is this union, and which itself is of course contained in X. So again, using that argument, this in fact is equal to this. So the sum that you see here is the sum where x varies over that z, and here x varies over y. And that same argument applies here also, that this sum becomes equal to this sum. Here also, the set of those values in x, or those points in x at which g does not vanish, is a subset of the set of those points where either f does not vanish or g does not vanish, which itself is a subset of x. So this sum, which is the intermediate one, where the set over which you are considering the sum is the z, set z, and this one is the sum where the set is y, and of course you have that other sum where the set is x itself. Okay, so that is the justification. But now we are almost there, because by the definition of such sums, this is just as x varies over x, and this one again by definition of the value of such a sum when it is absolutely convergent, this one is this. So that's how you have the part A, the first part. Since our original set x can be any set, so we have to use this definition for the value of the sum only. We do not really know whether x is at most countable or not. X may be uncountable also, and still the sum may be absolutely convergent. Although we have not come across any such actual sum in which the set over which you are considering the sum is uncountable, but such sets exist and such sums exist. And the reason we have so far not seen anything like that is because so far we have not in fact come across an actual uncountable set. We will do that it will come in the next few sections. The set of real numbers is uncountable. We will see. Okay, so anyway, so we have completed the proof of part A. Now let's see the proof of part B. Okay, so first of all, we have to prove that the sum of c times f of x as x varies over x, that sum is absolutely convergent for any real number c. So just like this one, let's start by considering a finite subset A of x and then looking at the corresponding finite sum. For any finite subset A of x, we look at this sum. Okay, so this one is just simply the absolute value of an ordinary product of two real numbers. So this is the product of their absolute values by elementary properties of absolute values. And then because this is the finite sum, you can take the absolute value of c common out by using one of the properties of finite sums. But now you remember that S1 is the supremum of all such sums as A varies over the collection of all finite subsets of X. So this thing is less than or equal to S1, and that is why this will be this, less than or equal to this, and definitely this is less than infinity. Note one more thing carefully, that the original inequality is this. And to get this inequality, you have to multiply on both sides by the absolute value of c. Can you do that? Yes, you can do that, because this is non-negative. That's why the inequality preserves its direction. Had it been a negative real number, the inequality would have reversed. Okay, so that the fact that we are considering the absolute value plays a role here. But anyway, so now these kind of sums all are less than or equal to this. So the supremum of them will also be less than or equal to this product. Hence, A is finite is less than or equal to this. This is one upper bound and supremum is the least upper bound. That's why, naturally. So that means our series or sum is absolutely convergent. Okay, but the job is not over. We have to now deal with the value. So now two cases arise according to whether C is non-zero or C is zero. So let's consider the zero case first. If C is equal to 0, then you just straight away apply the definition of this sum. Again, just like before, always keep in mind when you don't know what the set X is, or even if you know what the set X is, that in order to consider the sum, you have to write one such sum in which you consider only the non-zero values, because that is the definition. By definition, this is the value of this sum. But you see that since C is already 0, can you find any x in X for which this will become non-zero? No, such an x cannot be found. Such an x does not exist. So the set that you are looking at here, over which x is varying, is the empty set. The empty set is not, you should not write it in a way that it looks like the Greek letter phi. You just write 0 and then strike it. Okay, so this is an empty sum, so that by definition of finite sums where the set is empty, this is equal to 0. This comes from the definition itself of such sums. You go back to which section? Is it 7.1? Maybe. There you have definition of finite sums. So there you will get this. But this is just 0 times this value, whatever this value is. It is after all a real number, because this series is, or this sum is absolutely convergent. But 0 is C. So that's how our claim that this sum is equal to this sum. In other words, you can take C common out, even in this most general case. Now let's go to the case where C is non-zero. Now assume then again the starting is just like this. Okay. Now see, we have already proved that this sum is absolutely convergent, and because of that we have been able to use the definition of the value of this sum and write this. And we also know that this set, that is the set of all x such that C times f of x is not equal to 0, is an at most countable set. That means this set is either finite or countably infinite. When this set is finite, you are looking at a sum over finite set. And by that property that we already have of such sums, you can take C common out. And even when this set is countably infinite, and hence you can turn this sum into an ordinary infinite series by choosing a bijection between n and this set, because it is countably infinite. In that case also C can be taken outside, because that is one of the properties of ordinary infinite series. So that's why, due to the at most countability of this set, C comes out. So you can write C times, if you want you can you can write these equations like this, in this fashion, as an equation array, and beside this step, that is this next step, that is this one, first step, second step, you can write that explanation or that justification within brackets. I am not writing that here. Okay, why C comes outside that thing? And in fact, you can, if you really justify that by writing those things within square brackets, you can refer to the actual numbers of those results, proposition, this number, that subdivision. You can do those things. Okay. Now note that since C is non-zero, so C times fx is not equal to 0 if and only if fx itself is not equal to 0. So non-zeroness of C has made this product such that its own non-zeroness now depends on the f value being non-zero, and when the f value is 0, it becomes 0. So everything now depends on the f value. That is why this is also equal to this sum. In other words, what we are saying is that not just that the sums are equal, but actually the sets themselves are equal. The set of all x in X for which C times fx is non-zero is equal to the set of those values in X at which f is non-zero. But this is the definition of this sum itself. So that's how, in this case where C is non-zero, also we have this same thing, and hence our claim is established. And let me abruptly end things here itself. We will prove parts C and D next Sunday. And when do we have the next upload? This coming Tuesday. No? So we have already once again gone through graph theory. So on Tuesday, let's go back to group theory from Herstein's topics in algebra. So see you on Tuesday with that thing. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.